Welcome back. Today we're going to be moving on to the second part of our unit for systems of equations and inequalities. And today we're going to take a look at linear inequalities in two variables. Now, before we move on to our examples, we need to talk a little bit about linear inequalities, and I'm going to do that using an example. So the speed limit on a highway is 100 kilometers per hour, and a car is breaking the speed limit. This means that the speed s, so that's our variable s, at which the car is traveling is given by the inequality s is greater than 100, because the speed is bigger than 100. Now, when we're writing inequalities, we have to have one of the following symbols. So we can have less than, we can have greater than, we can have less than or equal to, and we can have greater than or equal to. When we're reading inequality signs, we always read from left to right. And so a less than symbol looks like an L tipped on its side. And then greater than is opening in the other direction. And as we learned in previous years, when we're talking about values being included or not included, we would have open dots and closed dots. So for example, if I wanted to say that x was greater than 3, and I drew this on a number line, I would draw my point at 3. X is greater than 3 would not be included, so I would draw my line. If I wanted to show that x was less than or equal to -1, I could draw my line, put a point at -1. This is included, and then I would have everything drawing down this way. Now we're going to be moving on and talking about linear inequalities in two variables, meaning that we're going to have two variables in our inequality. So some examples, we have y is less than or equal to -15x minus 10. 3x plus 2y is greater than 5. And then we have 4p minus 2q is less than 8. Notice that in all cases we have inequality signs and not equal signs. Now, an ordered pair x comma y is a solution to a linear inequality if the inequality is true when the values of x and y are substituted in. And that's going to come into play as we start working through our examples. Now, the solution region to a linear inequality in two variables can be represented on a coordinate plane using a boundary line. So if we go back to up here where I had our linear inequalities in one variable, we had open dots and closed dots, or open circles and closed circles. Now we're going to be dealing with boundary lines. So a boundary line can be solid if we have greater than or equal to or less than or equal to symbols. So a solid line would occur when those values are included. And a broken line or a dotted line would be used if we had greater than or less than. Now, before we move into our examples, let's take a look at how we would graph a linear equality in two variables. There's just a few steps. The first thing we're going to do is graph our linear equation, and we're going to make sure that we use the appropriate boundary line. So again, if it's included, we would have a solid line. If it's not included, we would have a broken line. Then we're going to pick a test point, and it doesn't matter what test point we pick, because if we substitute it in and it makes the statement false, then we would shade on the opposite side. If we plug in a test point and it's true, then we know that's the side that we can shade on. So we're going to select our test point, we're going to determine whether it makes the statement true or false, and then we're going to shade the appropriate region. Now, when it comes to graphing our inequalities, there are going to be times when we have to rearrange our equation so that it says y is less than or y is greater than. And sometimes that will involve dividing by negatives. So remember, whenever we have to multiply or divide by a negative, the inequality will change direction, so it will flip. Now, taking a look at our first example, we're asked to graph the inequality y is greater than 3 over 4x plus 3. Well, the first thing I'm going to notice here is that this inequality sign does not have an equal to symbol, so this is going to be a broken or a dotted line when we draw our boundary line. So we start off by plotting 3 over 4x plus 3. We can do that by finding our y-intercept of 3 and plotting our slope of 3 over 4. So up 3, right 4. Now, if you've forgotten how to do this, you can also create a table of values. And you can also use your calculator to double check. Now, once we have those points plotted, we're going to pull out our ruler, line up our dots, and draw our boundary line. Again, remembering that this is a dotted or broken line. Now, once we have our boundary line drawn, we're going to choose a test point, and I typically choose 0, 0, so I choose the origin. The only time that I would not be able to do that is if that point falls on the boundary line. So when we're checking test points, we want to make sure that we pick points that are not on the boundary. All right, so my test point here is 0, 0. And I'm going to sub that into my inequality. So I have y, then I have 3 over 4x plus 3. So subbing in my values, I have 0 equals 3/4 times 0 plus 3. Well, 3/4 times 0 is 0. 0 plus 3 is 3. So I have 0 and 3. And when I look at that statement, 0 is greater than 3. This is a false statement. So this is not true, meaning that 0, 0 does not fall within the solution region. So I'm instead going to shade this side. Now by shading this means that any values or any coordinate that falls in the shaded region would be a solution for this inequality. So let's just check that out. Let's take the point 0, 10, and we're going to sub it in and see if it makes our statement true. So our y value is 10, and then we have 3 over 4 times 0 plus 3 gives us 10 and 3. Well, it is true that 10 is greater than 3, so that works. We might pick a different point here. Let's choose -4 and 4. So if I sub those in, I've got -4, 4, setting up my inequality. Y is 4, and then I've got 3 over 4 times -4 plus 3. Well, 3/4 times -4 is going to be -3, so I have 4 equals -3 plus 3, which is 0. Well, it is true that 4 is greater than 0, so again, this is a solution. So moving on to example 2, we're asked to graph 3x minus 3y is greater than or equal to 12. Well, we have that equal to sign there, so we know this is going to be a solid line. And in order to graph this, we're going to have to rearrange our inequality. So we're going to have -3y is greater than or equal to -3x plus 12. And to get y by itself, we're going to divide by -3 on both sides. So that leaves me with y is less than or equal to x minus 4. Notice that my sign had to change because I divided by a negative. Now, some people find that a little bit daunting to have to remember just one more rule. So another way to get around that is to always move your y so it stays positive. So taking a look at that here, if I had 3x minus 3y is greater than or equal to 12, so I would have 3x minus 12 is greater than or equal to 3y. Dividing by 3, I'm going to have x minus 4 is greater than or equal to y. Now we're still going to have to rewrite that inequality. We know that y is the smaller value, so we have y is less than or equal to x minus 4. So both methods work, but you just have to remember if you're dividing by a negative, your sign has to flip. So plotting our inequality here, we have y is less than or equal to x minus 4. We're going to start by plotting our y-intercept at -4, and then we have a slope of 1. So we're going up by 1, and so on. We don't have to necessarily list all those points. Now using our ruler, we'll line those up with the dots. And again, as we're plotting this, we're going to use a solid line because those values are included on the boundary line. And then we choose our test point. Once again, I'm going to choose 0, 0 because it does not fall on our boundary line. So my test point here is 0, 0. And we sub that into our inequality. So I'm always going to go back to my original just in case I've made some calculator errors. So I have 3 times 0 minus 3 times 0, and that gives me 0. Well, it's not true that 0 is greater than or equal to 12. That's a false statement. So my test point is at the origin. That's not a true statement. So that means my shaded region is below the line. Now, taking a look at example number 3, we're asked to graph 5x minus 20y is less than 0. Taking a look at our inequality, we know that we're going to have a broken line. And then we rearrange our inequality. So I have -20y is less than -5x. We want to get y by itself. We're going to divide both sides by -20. So I'm going to have y is greater than x over 4, or another way to write that is y is greater than 1/4 x. So my y-intercept is going to happen at 0, and my slope is 1/4, so up 1, right 4, up 1, right 4. Now once again, we're going to grab our ruler and we're going to line it up with our dots. We're going to make sure that our boundary line is dotted or broken. And then we're going to pick our test point. Now notice this time our boundary line goes right through the origin, so we cannot choose that as one of our points. So instead I've chosen to use 0, 10. Often I'll choose numbers that are fairly easy to do in my head. So checking that out there, we've got 5x minus 20y, and we have 0. So we're going to have 5 times 0 minus 20 times 10 gives me 0 minus 200, so negative 200 and 0. And we have negative 200 is less than 0. Well, that's a true statement, so that tells me that 0, 10 is included in the solution region, so this is the side I'm going to shade on. Now, before we move on to our next examples, I want to show you that you can also check these on your calculator. So we're going to move back to example number 2, where we have 3x minus 3y is greater than or equal to 12. On our calculators, the first thing we're going to do is enter our equation, which in this case is y is less than or equal to x minus 4. Well, we're going to enter the x minus 4. And then to make an inequality, we're going to actually arrow over to the symbol on the left-hand side of the y value. As we hit enter, this is going to cycle through a number of different options that we have. And so our first line, that's our original one that's always there, is just a thin solid line. We have a thick line and so on. Well, we want to graph y is less than or equal to x minus 4. So that means we're looking for the less than symbol, which really looks like an L. So we're going to hit enter, enter. This would be the symbol for greater than, and this is our symbol for less than. And so when we graph our equation, we're going to see y is less than or equal to x minus 4. Now, moving on to example 3, we're going to graph y is greater than 1/4 x. So on our calculator, we're going to graph 1 over 4x. And we want the greater than symbol this time. So that's going to be this one here, where the shading is up top. And again, we'll hit graph. And we should notice that we have the same shape and shading as we had on our paper. So just as a recap, if I'm looking for less than, the symbol is going to look like a filled in L on my calculator. And if I'm looking for greater than, I'm going to have this other triangle that's filled in. Now we can be asked to graph inequalities, but we can also be given a diagram and asked to find the equation and hence the inequality that's being graphed. So to do that, we're often going to have to find the equations of lines. And so going back to grade 10, we have some formulas that we used. First of all, we have our slope formula, m equals y2 minus y1 over x2 minus x1. We have our slope formula of y equals mx plus b. Remember that m stands for slope and b stands for our y-intercept. We also looked at the point slope form, so we have y minus y1 equals m times x minus x1, and our point would be at x1, y1, and m would still be our slope. Now the last equation is general form, but that's one you don't see too often with these particular examples. All right, so the diagrams below show the solution region to an inequality. We're asked to determine the equation of the boundary line and then determine the inequality. And so we're going to start off by finding the equation of that line. So taking a look at some points here, we know that our y-intercept is happening at 0, -3. And we have another point here at -1, 0. So that's our x-intercept. So we start off by using our slope formula. If it helps, you can always label your coordinates x1, y1, x2, y2. And then we have our formula, y2 minus y1, so 0 minus -3, and -1 minus 0 gives us a positive 3 over -1. So we have a slope of -3. Now our y-intercept is happening at -3, so the equation of our boundary line is y is equal to -3x minus 3. But now we have to decide, is it greater than or is it less than? We do know that we have a dotted line here, so we know that it's not going to be equal to. So we choose a test point, and in this case I chose one that was in the solution region. You could choose the origin, but then you have to remember that that's not in the solution region, and then you'd have to also remember to switch your signs. So when we're doing these types of questions, it's often easier to pick a solution or pick a test point that's within the solution. So I chose to use -3 and -1. So I've got my test point here of -3 comma -1. We've set up a chart. We've got y on one side and -3x minus 3 on the other. We sub in our values, so we have -1 and then -3 times -3 minus 3 gives us 9 minus 3, which is 6. Well, -1 is less than 6. And so that tells us that y is less than -3x minus 3. So our inequality will be y is less than -3x minus 3. Now we can certainly check this on our calculator. So we start by graphing our equation, -3x minus 3. We want the inequality to be less than. So I'm going to hit enter, enter, enter. Make sure you don't hit your enters too quickly. You'll end up kind of buzzing past what it is that you need, and then you have to go back through the whole menu again. So graphing our inequality looks very similar. We just want to double check some of our points. So I can trace at 0, and that gives me 0, -3. I can trace at -1, and that gives me -1 comma 0. Both of my points match, my shading's on the right side, so I can be confident that my inequality is correct. Moving on to our next example, here we have a solid line, so we know this is going to be either greater than or equal to or less than or equal to. We're going to start off by finding the equation of our boundary line, so I have my y-intercept at 0, 4, and then I have another point here at -3 and -5. So I'll start off with my slope formula again. I'm going to have -5 minus 4 divided by -3 minus 0. So that gives me -9 divided by -3, which gives me a slope of 3. Again, I lucked out because I saw what my y-intercept was, so I know that my b value will be 4. So my equation for the boundary line is y equals 3x plus 4. Once again, we're going to choose a test point to see what our inequality is. Now, in this case, I lucked out. Origin is in the solution region. So my test point will be 0, 0. Setting up my equation, I've got y and 3x plus 4. So we sub in 0, and then 3 times 0 plus 4. So 3 times 0 is 0 plus 4 is 4. Well, 0 is less than or equal to 4. Notice I included the equal to because this is a solid line. So my inequality will be y is less than or equal to 3x plus 4. Again, we'll go on to our calculator and check our answer. So we type in 3x plus 4. We want y to be less than or equal to. And again, we want to double check our points just to make sure our equation is correct. So we're going to trace at 0, gives me 0, 4. I'm going to trace at -3. That gives me -3, -5, so I know that I'm correct. Now for our last example, we're going to take a look at an application. So in this example, you would like to make a mosaic using tile and stone. Now tile costs $2.50 per square foot and stone costs $7.50 per kilogram, but your budget is $60. So the reason this is an inequality is because when we're talking about budgets, we want to make sure that we spend $60 or less. So we want to make sure that our value or our costs are less than or equal to 60. So the first thing we're going to do is set up our variables. And so I have T for tile and I'm going to use N for stone. So T is going to be the amount of tile. and N is going to be the amount of stone. Now you could certainly use an S, but I find that my S's look too much like 5s. So setting up our inequality, we have 250 per square foot for T. So we have 250 T plus 7.5 or 750 N has to be less than or equal to 60. So it can cost $60, but it can't cost any more. Now, for the purposes of this question, I've made T my X value or my independent variable, and I've made N my dependent variable. Simplifying my formula, I have 2.5 T plus 7.5 N is less than or equal to 60. Now rearranging, because I have N set as my Y variable, I'm going to rearrange so that I have N by itself. So that's going to give me 7.5 N is less than or equal to negative 2.5 T plus 60. I'm going to divide by 7.5 on both sides. And that gives me N is less than or equal to negative 1/3 T plus 8. Now I can certainly graph this on my calculator, but it would be quite easy to figure out my X and Y intercepts. So I'm going to do that just so I have an idea of my window range. So I know based on this inequality that my Y intercept is going to be 8. So that means I don't need to go any higher than 8 for my N values, but I'm going to check out my X intercept. So I'm going to sub in 0 for N, and that's going to give me negative 1/3 T plus 8. Getting T by itself, I'm going to have negative 8 equals negative 1/3 T. If I divide by negative 1/3 on both sides, I'm going to have T equals 24. So I know as I graph this that my y-intercept is going to be 8 and my x-intercept is going to be 24. So I'm going to go up by 1s. And I'm going to go up by 2s for T. And I know that those are my 2 points. Once again, using my ruler, I can draw my line. Now you can probably assume which side is going to be your solution region, but we still want to take a test point just to check. So I'm going to make my test point 0, 0. And if I sub those in, I'm going to have 0 plus 0 is less than or equal to 60, which is true. So 0, 0 falls within my solution region, so I can shade this section of the graph. Now you'll notice in this question, our boundaries go no less than 0. And that's because of the context of the question. We can't buy negative tiles or negative amounts of stone. So if I were to have to give the domain and range of this function or this inequality, I would say that my t values fall between 0 and 24, and my n values fall between 0 and 8. Now in the question, we're asked to state some possible combinations of tile and stone that could be used to make this mosaic. So any coordinates that fall within the shaded region would be solutions. So I went up by 2s here, so I might have 4 tiles and 2 stones. Or I could have 2, 4, 6, 8, 10. I could have 10 tiles and 3 stones would work. So any values that fall within the shaded region would be valid solutions, except I wouldn't pick decimals because I can't go and buy like 1.25 tiles. Now, if I want to graph this on my calculator, I'll start by graphing the inequality. So I have negative 1/3 x plus 8, and my inequality is less than or equal to. But in order to make my graph look like what I have on the side here, I'm going to have to adjust my window settings. So we notice that our minimum x value is 0 and our max is 24. So I'll go into my window settings. I'll go from 0 to 24. I might go a little bit higher just so that I can see more of the graph. So I'll go up to 30. And then I'm going to go from 0 to 10 and go up by 1s. And so this will give me a much better visual of what my inequality is. Now, if I move my cursor up and down, anything that's in the non-shaded region is not a solution. anything in the shaded region is a solution. So for example, 6 tiles and 2 stones would be a valid solution. 3 tiles and 4 stones would work. Those would all be answers. Now, if I'm right on the line, I could have 0 tiles and 8 stones. That would work. If I had 24 tiles and 0 stones, that would work. So any value that's on my line is also a solution. All right, so that gives you a number of examples for inequalities. Again, the steps are fairly easy. Start off by graphing your line, find that test point, and then shade. So if you want to get out your pencil crayons or have some fun with your coloring, this is the time to do it. All right, thanks guys. Have a great day and we'll see you soon.